Hey Condors, it's your boy Mr. Roberts here with another episode of Social Distancing Science. Hey, before we get started, don't forget, hit that subscribe button and mash that bell so you don't miss a single episode of Social Distancing Science. Let's check out our agenda for today. Got a few things we're going to do. Nothing too hard though. We're going to do a little reading. What is gravity's role in the formation of stars? We're going to do a lab about changing shape. We're going to read about what's the role of gravity in the formation of the solar system. We're going to do a little 3D thinking about that. We'll do a lab about elliptical orbits, and we're going to read about how does gravity affect objects that orbit the sun. Let's get started. So just as the force of gravity pulls a basketball to the floor, the force also pulls dust and gas inward in space. What impact does this have on objects in the universe such as galaxies and stars? Let's find out. Now, when gas and dust clump together and form nebula, the particles bump into each other and move faster. Gravity makes these nebula hotter. As the particles are pulled closer together as a result of gravity, they start to bump into each other and cause them to move faster, which causes the temperature increase. The hotter something is, the more quickly its atoms move. As atoms move, they collide. If a gas is hot enough and its atoms move quickly enough, the nuclei of some of the atoms combine. Nuclear fusion is a process that occurs when the nuclei of several atoms combine into one larger nucleus. Once nuclear fusion has occurred, a star is formed. Okay, let's learn about changing shape. Now, when the solar system formed, it was an enormous ball of gas and dust spinning slowly in space. As gravity pulled it closer together, the solar system spun faster. What happened to the shape of the solar system as it spun faster? Let's find out. We're going to need salt dough. Ta-da! A small bucket. Ta-da! And I've already put string on it. So I made a round salt dough, and let's go ahead and place that in the small bucket. Okay? I'm going to step back and I'm going to whirl the bucket, and we're going to see what happened to the salt dough. Hey, just so you all see, it's nice and round right now, right? What do you think is going to happen as it gets whirled? Ooh. Let's go to the classroom and find out. Okay, I'm going to back up a little. I'm going to try not hit anything, especially not any students. So I've got this bucket with my salt dough in it, and I'm going to start spinning it. And let's see if that was enough. What happened to our salt ball? Is it still round? No, it kind of got squished. Let's make some observations. So, put your observations here, and let's go answer some questions. So, what happened to the salt dough? What other objects change shape as they spin? How do you think gravity influenced the shape of the early solar system? Answer these questions, and we'll continue on. So, let's read. What is the role of gravity in the formation of the solar system? The solar system formed from a rotating cloud of gas, ice, and dust called a nebula. Gravity caused the cloud to collapse inward. Because the cloud was still rotating after the collapse, it flattened into a disk, much like our piece of salt dough. Gravity pulled gas and dust towards the center of the disk, forming the sun. Next, the planets began to form as gravity pulled these small particles together. As they collided, they stuck to each other and formed larger, unevenly shaped objects. These larger objects had more mass and attracted more particles. Eventually, enough matter collected and formed Earth and the 7 other planets. The leftover large particles formed into moons that orbit the planets. Asteroids orbit the sun in the asteroid belt, while meteoroids, dwarf planets, and comets orbit the sun in their own paths through the solar system. So it went from a solar nebula to a disk forming, to a planet forming, to the solar system today. Okay, let's do a little quick 3D thinking about this. So, using what you know about how the solar system formed, construct an explanation of how other solar systems in other galaxies formed. Pause the video, answer this, and come on back. Because we're going to do another lab on elliptical orbits. Have you ever swung a ball on the end of a string in a circle over your head? In some ways, the motion of a planet around the sun is like the motion of that ball. As shown below, the sun's gravitational force pulls each planet towards the sun. This force is similar to the pull of the string that keeps the ball moving in a circle. The sun's gravitational force pulls on each planet and keeps it moving around a curved path around the sun. So, with the gravitational pull, oh look, the Earth orbits the sun. What happens without the gravitational pull? There's Earth, and there it goes. But unlike the ball on the string, planets do not move in circles. They move in an elliptical shape. Let's investigate those orbits. We're going to need some materials. I've already got them. Okay. I've already done this. I've cut a piece of string. I've put my push pins into a board. Let's see what happens. You're going to be recording observations. Let's go to the classroom and look what we have here. Okay. I have a string here. It's 24 centimeters, and I'm going to put it on. So I put it on the two pegs that are 8 centimeters apart. Let's see what happens when we use a pen and we stretch the string out and we draw. There we go. Okay. What kind of shape do you think we're going to get? Oh, an elliptical shape. Now, what do you think might happen if we change from being the ones that are so far apart to ones that are slightly closer? I'll use a different color Sharpie for this. Oop, let's go back around. Huh. We have 2 different shapes. Okay, let's go back to the curriculum. So, let's see. We need to measure the maximum width and length of the ellipse. Let's go ahead and do that. I'm going to grab a tape measure. Oops, my tape measure was in inches. So I went and I grabbed a ruler. Let's measure the maximum width and length of the ellipse. So here we have it. Let's see. The ellipse has a length of 12 centimeters and a width of 8.5. Okay. And let's just go ahead and measure for the larger one. For the larger circle, we end up with a diameter of about 15.5. Let's go to our questions. So, can you record your data and your observations? And let's analyze and conclude. How would you compare and contrast the 2 ellipses? And let's just do a little reading and we're done for today. So how does gravity affect objects that orbit the sun? Earth was once thought to be the center of our solar system. In this geocentric model, the sun, the moon, and the planets revolved in circular orbits around a stationary Earth. In the early 1500s, Nicholas Copernicus proposed that Earth and other planets revolve in circular orbits around a stationary sun, a heliocentric model. So in the 1600s, Johannes Kepler discovered that planets' orbits are ellipses, not circle. An ellipse contains two fixed points called foci, the singular of which would be focus. Foci are equal distance from the ellipse's center and determines its shape. The sun is at one focus. As a planet revolves, the distance between the planet and the sun changes. Kepler also discovered that a planet's speed increases as it gets nearer to the sun. Why don't all celestial objects in the solar system orbit the sun? Remember, the gravitational force between objects depends on mass and distance. So, the moon orbits Earth because the gravitational attraction between the moon and Earth is stronger than the attraction between the moon and the sun. That's it for today, folks. Hope you're having a great day. I will see you all later.